Hello, advanced algebra students, and welcome back to our first video lesson for chapter 7 as we begin to explore the power function and the key features of power functions, the difference between even and odd power functions, and how do we use these in what we might call modeling them or real situations. And so Friday you were looking at these types of graphs, trying to graph y equals x squared or y equals x cubed, or the negative versions of that, and just trying to come up with some patterns that might exist. So hopefully you noticed a couple of things. First of all, the domain for all power functions, if you notice, the domain in all of these examples is all real numbers. Okay, the domain will always be all real numbers. And that's just how we have it set up because of the x. The range, however, is slightly different for each one, okay? And there's some patterns here, right? X squared or x to the fourth or negative x to the fourth, negative x to the sixth. Notice the ending on those is pointing in the same direction, right? The ending on each of those graphs is either both pointing up or both pointing down, which means that changes the range. Whereas these x to the third, x to the fifth, negative x to the seventh, negative x to the third, things like that, one ending is pointing up, one ending pointing down. And when that happens, the range is also all real numbers. And we're going to talk about some key characteristics here, but notice the difference in these is whether or not they are even power functions, x squared, x to the fourth, negative x to the sixth, or are they odd power functions, x cubed, x fifth, negative x to the seventh. Okay, and so there's some key differences in those, and that's what we got to pay attention to, is whether or not we are dealing with even versus odd power functions. So an even power function, when we are dealing with even, it's going to, especially if it's a positive even, is going to open up and have two endings pointing up. So the symmetry here will always have a line of reflection, okay? It'll be a reflection of x equals 0. We will always have a reflection line on the y-axis, which has an equation, y equals 0. The domain will be all real numbers. And because it's all real numbers, right, the x goes both ways. Now, what is the range? The range, again, is slightly different because it doesn't go up and down. In this case, when it's a positive even, the range has to be greater than or equal to 0. My y values will have to be greater than or equal to 0 because it's always going to go up in the positive directions. So what are two samples? Y equals x squared. Maybe this is y equals x to the fourth, x to the sixth, anything like that, okay? Now, when we have a negative sign out in front, and what we've learned from our quadratics is that turns the graph upside down. The only thing that changes, though, from up on top is the range. The range now becomes different. The range is going to be y has to be less than or equal to 0 because all of these numbers are going down. And that's the only property that changes with even power functions. Now, if we look at the odd power functions, this one's a little bit different, okay? The odd power functions have a graph that starts in one quadrant, goes through the origin typically, and then goes down to the opposite quadrant. It's really hard to graph, okay? But this symmetry has a rotation. It's not a reflection. This instead has a rotation about the origin. And so we write that its symmetry is a rotation about the point 0, 0. Meaning that if I had a point up here that was 2 over and 4 up, I'd have to go the opposite direction then, 2 and 4 down to get the exact same point. That's that rotation. The domain, all real numbers. The range, also all real numbers, okay? And this is for odd. The key here is that it's odd. Examples, y equals x to the third, x to the 11th, whatever you wanted to put for an odd number. Now, the minute we put, though, a negative symbol out in front, okay, once we put a negative symbol out in front, there's not really any property changes. The properties all here stay the same. It's just that we start in the second quadrant and go down to the fourth, okay? We start in the second and we go down to the fourth if it's that negative part. And so if it is a positive x to an odd number, we go from quadrant 1 to quadrant 3. If it is a negative x and odd power, we are going from quadrant 2 to quadrant 4. And that's the only difference in the odd ones. Otherwise, domain and range are all the same. Okay, so that's the general idea of what you were looking at the other day. And what happens as we're looking at this is, how do I transpose or move different points, right? If AB is a point on a power function, AB, meaning A, B, right here, well, that means if it's an even one, remember evens have to look like this. So the point would have to be over here, and we use our knowledge about what are the points in the second quadrant. Well, the first one is negative, but the second one is positive. So it would have to be negative AB over here. Whereas in an odd, if I graphed AB, because, AB, they're both positive, we know that it's going to have to go down here to this quadrant somewhere. Right, quadrant 1 to quadrant 3. Well, what are the points down here? They're both negative. And so we can sort of draw them out, in a sense, to help us figure out where they should be located. Okay, and that's really what's key in some of this stuff. Like if they give us a point, negative 3, comma 81, how can we figure out if that's even or odd? And then what equation would we use? Well, remember, we always write points as x comma y. And if this is x, we're only working with power functions, x to the power of some number. So if I did negative 3 squared, well, that would give me a positive 9. If I did negative 3 to the third, that would give me negative 27. And if I did negative 3 to the fourth, that would give me 81. So I know this has to be an even. Now, I knew that as well, because if I take a negative number and give it to any power, and I get positive, that would be an even. The equation is still right down here, right? The equation would be negative 3 to the fourth equals 81. We should put negative 3 in parentheses. Right, and so we can kind of use some of that knowledge to help us go back and forth. But really, the point in all of this is to help us with what's coming next, okay? I think we know how to graph these nth powers. We can use tables of values. We can also use Desmos. And I think we can compare and contrast them. But now it's more about this solving. This is where we're getting into in Chapter 7. More about probability of things happening, okay? In an event that has a probability of P, right? Like flipping a coin. It has getting heads is 1 out of 2. If each occurrence of the event is independent, meaning it doesn't rely on the previous one, then that probability of the event occurring n times in a row is P to the power of n. So we look at the probability of it happening one time, and how many times do we want it to happen? Let's look at an example. Rolling a die and getting a 4 3 times in a row. What is the probability of rolling a 4? Let's just look at it once. The probability of rolling a 4. That's 1 out of 6 on a die. There's one number 4 on the 6th side. So I have a 1/6 chance at getting a 4. What's the probability of me rolling that 3 times in a row means I can take this to the 3rd power. 1/6 to the 3rd power, which means that probability of that happening is 1 out of, oh goodness, what's 36 times 6? This is where you need a calculator, or you just need to be probably a little bit smarter than I am today. 216. 1 out of 216 times it should happen that you roll a 4 3 times in a row. What is the probability of flipping a coin and getting heads 5 times in a row? So you flip it once. What's the chance of getting a heads? 1/2. How many times in a row do I want to do that? 5. 1/2 to the 5th. 2 to the 5th is the 32. So 1/32 of a chance. 1 out of 32 times you should get 5 heads in a row. I don't know that, and these are what we call theoretical probability. In theory, this is what should happen. If we were to practice this, we could get different numbers. What's the probability of randomly guessing on the first 10 ACT math questions, the first 10 of them, and getting them all correct? Well, those of you that just took the ACT math, there was 5 answers. So guessing would give us a 1 out of 5 chance, because there was 5 possible answers to choose from, and we needed to guess 10 times in a row. So 1/5 to the 10th, right? But the idea here is that these are independent, right? I don't need to rely on the first one to get a result. Like I don't need to pick an ace and then pick another ace out of a deck of cards. And so let's see what this means for our last one today. What is the probability of answering 5 consecutive true-false questions correct? Okay, well, what's the probability of you getting 1 true-false question correct? If you just guess 1 out of 2, you have 2 choices. You could guess true, or you could guess false. Okay, and that means you have a 1 out of 2 chance in getting it correct. And therefore, if there's 5 of those, that means I'm going to do that to the 5th power 5 times, which would be 1/32. You'd have a 1 out of 32 chance in getting all 5 of those correct. So that's the idea behind these power functions. We're going to start to use them in terms of probability and relationships. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe.